Hello everyone. In this video we're going to be simplifying a radical expression, a very radical expression. We have the fifth root of 5 root 5 plus 11 divided by 2 plus the fifth root of 5 root 5 minus 11 over 2. Alright, so in some sense we could also use the call this a golden radical somewhat. You'll notice why. But anyways, we've seen a lot of some of square roots, some of cube roots, but this time we have fifth roots. All right, I'll be presenting two methods, and let's start with the first one. My first method basically involves substitution. So let's go ahead and call the first part of this expression, or first term here, a. So I'm going to call this a, and let's go ahead and call the other one b. All right, so according to my assumption, the fifth root of 5 root 5 plus 11 over 2 is equal to a, and the fifth root of 5 root 5 minus 11 over 2 is equal to b. Great. Now from here we get something really nice. If we raise both sides to the fifth power for both a and b, we get a to the fifth power equals 5 root 5 plus 11 over 2. And b to the fifth power equals 5 root 5 minus 11 over 2. Now, why is this nice? Because if you add these two equations together, 11 is going to cancel out. We're going to have something nicer. So let's go ahead and add them. A to the fifth plus b to the fifth. I know some people are going to recommend subtracting them, and obviously you can go that route too. If you add these up, you're going to get 5 root 5. And 11 is going to cancel out. You're going to have this twice divided by 2. So in other words, the answer is going to be 5 root 5. So we have two numbers whose sum of fifth power is equal to 5 root 5. If you can find another equation for a and b, then we should be able to solve this as a system. So that's the whole idea. Obviously, second method is different from this. So the other idea is, since these expressions are, I know if I say conjugates, people are going to say they're not conjugates, but you get the idea. They're kind of like x plus y and x minus y. They're in that form. So if you multiply them, we're going to get something nice. So let's go ahead and take a look at a times b. A times b is going to be the fifth root of the product of these two expressions. Let's go ahead and write them under the same radical. All right. And from here, we're going to get a difference of two squares. Let's multiply these together. So 5 root 5 squared is going to be 25 times 5, which is 125. Minus 11 squared is 121. That divided by 2 times 2, which is 4. And then I have to take the fifth root of that. And this is going to be 1, as you can see here. So we got a really nice system here. We have a to the fifth plus b to the fifth equals 5 root 5. And we got ab equals 1. So is that good enough? Let's find out. Obviously, I'm going to have to expand some of the stuff here so that I can use, some of the algebraic formulas or identities. Great. So let's go ahead and do something else here. We call the first thing a and the second thing b, but what are we trying to find here? Let's call that x. So that the whole thing is x. So now we have a plus b is equal to x. And what I'm going to do is raise both sides of this to the fifth power. When I do, I'm going to get some extra terms, but we'll take care of them as we go. Okay, so let's raise both sides to the fifth power and use the binomial theorem. And remember, we just recently used binomial theorem, and binomial theorem is awesome. And remember the Pascal's triangle, the 1, 5, 10, 10, 5, 1? Kind of like a 5 choose 0, 5 choose 1, how we obtain these binomial coefficients, so on and so forth. Hopefully you know the story. If not, just look it up. So we get the coefficients for the fifth row. And I'm going to write it up, expand this. But when I expand this, I would like to put the like terms together. So I hope you don't mind. Or I can do that later. How about this? Let's go ahead and expand it, and then we'll do that later. So I don't want to rush. Okay, so 1, 5, and then I have a 10. Notice that the powers of A are decreasing, and B is increasing. And there's a really nice symmetry here, and this is going to be x to the fifth power. So now that is the binomial theorem, but I would like to put these two together. Obviously, that makes sense, right? Because we want to, we know a to the fifth plus b to the fifth. And then, of course, these two go well together, so let's go ahead and put them together. But take out 5ab, That's going to give us a cubed plus b cubed. And then these two should go together, and we can take out 10a squared b squared, and that gives us a plus b inside the parentheses, and the whole thing is x to the 5th power. Great. So now I know a to the 5th plus b to the 5th, right? And then I don't know a cubed plus b cubed. Hopefully I can find out. I know ab is 1. This is 5 root 5. And then this is also 1 because you're just squaring it. And a plus b is equal to x. Remember that. So a cubed plus b cubed, I don't know what it is, but I can find it in terms of x. So let's go ahead and, just replace everything with what it is. And this, I don't know what it is, so I'm just going to leave it as is right now and then isolate it. And let's see. This is going to be 10x, right? And that is equal to x to the 5th power. Awesome. Now, at this point, we don't know what a cubed plus b cubed is in terms of x. We could find it, but I can also obtain it from a plus b. Because since a plus b is equal to x, let's do the following. I'm going to cube both sides. How about that? Let's go ahead and cube both sides here. Oops. I said cube, but I write 2. That's what mathematicians do sometimes. By the way, I'm not a mathematician, but anyways, I just gave myself that title real quick. So if you cube this expression, remember we're going to get from a famous identity a cubed plus b cubed plus 3ab times a plus b. That's an identity we use a lot. So now we can get a cubed plus b cubed from here because a plus b is x and ab is 1. So from here, a cubed plus b cubed becomes x cubed minus 3x. Okay, great. So this is something we can definitely use here. And when we plug it in, we're going to get a really nice Quintic equation. Well, Quintic equations aren't always nice, but this one is a really nice one. You'll see. Okay, so I'm going to do the replacement. The rest is just straightforward, hopefully. And then now put it together nicely. You're going to get x to the 5th power minus 5x cubed, and then plus 5x. Where that comes from, let me tell you. Negative 15x plus 10x, that's going to be negative 5x, but I'm putting everything on the right-hand side. I hope you don't mind. I skipped a step there. Sorry about that, but you can definitely work it out. I trust in you guys. And then this equation is, for some reason, becomes factorable, right? It's not magic, guys. It's been arranged. I know some people are going to be like, this problem is contrived. Of course. Most competition problems are contrived. By the way, this is not a competition problem. It's kind of homemade. I didn't call it homemade, I guess. But anyways, I talked too much, so I should stop. Okay, let's proceed. Take out x cubed. You get x squared minus 5. And then plus 5 times x minus root 5. And some people are like, how is this factorable or arranged? Well, if you look at x squared minus 5 from an irrational perspective, right, then you'll notice that it's factorable by difference of 2 squares. So I can write this as x plus root 5. It's not factorable in the integers, but for irrationals we have more options. Okay, so now x minus root 5 obviously stands out as a root, right? But let's take it out, and the rest is going to be x to the 4th power plus 5 root 5. X cubed, and then plus 5. Awesome. I get a really cool Quintic, and I know some of you might probably be thinking like, can I replace x with root 5 or maybe a times root 5? Maybe x is a multiple of root 5 in this case. It might be, because we had equations like this before, and it worked out nicely with root 2 and root 3, but bad news. Bad news. This equation, or maybe it's good news, who knows, right? No real solutions. How did I know that, right? I checked it for you guys. But here's the thing. At the end, I'm going to show you what the solutions look like, because some people are upset when I say, hey, no real solutions, and just discard it. But I'll show you what the non-real solutions are. Okay, great. So from here, we get one real solution, which is x equals root 5. And as you know, the Quintic equation, if the coefficients are real, it has to have at least one real root. Okay. So x equals root 5 is the only one that works, which means our expression, and remember we set it equal to x, so we solved for x and we got the answer, and the answer is root 5. Now, why did I say this might be called a golden problem? You'll notice we have to do the second method first. All right, let's go ahead and do the second method. I hope I didn't take too long. I'm not trying to rush, but anyways. So the second method is kind of interesting because it is going to deal with one of these radicals first, and I think we talked about this. I'm assuming that the fifth root of this radical is going to look like something like this, a root 5 plus b. And why I write the a root 5 plus b? Well, you could also write it as a plus b root 5, I guess, but anyways. So a and b are rationals in this case, and guess what? I'm going to raise both sides to the fifth power, because I want to get rid of the fifth root, right? Obviously. And let's go ahead and do this. When I do this, it's going to be messy, very messy. So let me go ahead and give you what's going to happen on the right-hand side. First, the right-hand side is going to give us the following. 25 root 5 a to the fifth power plus 125 a to the fourth b. Again, I'm using the binomial theorem, but with some radicals inside. So plus 50 a squared b cubed. And notice that one of them is irrational, one of the terms, and the other one is rational. So it kind of alternates. And this one is the right-hand side. And that is going to equal the left-hand side, but that's easy. Let's go ahead and rearrange the terms here. And when I put the terms with root 5 in it together, I get the following. I get these multiplied by root 5, and everything else is just, you know, rationals. All right? Remember, I didn't say integers, I said they are rationals. So now, since this expression is equal to 5 root 5 plus 11 divided by 2, but can I write it as 5 root 5 over 2 plus 11 over 2, so that I can compare the coefficient of root 5 and the constant term. I mean, constant, they're both constants, but, you know, it's the rational part. So now, we can safely say that, hey, this guy here should equal 5 halves, because they have to be rationals. So the coefficient of the irrational must be the same on both sides. And you can easily prove that it's the case. And this guy over here needs to equal 11 halves. This gives us a system, which is quintic, by the way. So not very easy to solve, but I'm going to show you. This is a special type of system. And we dealt with these while solving, what is it called? Differential equations. Yes, the idea of homogeneousness. Did I say that right? Okay, something like that. Homogeneity, is that a word? But anyways, those are hard words. So 50a squared b cubed. Yep, that is equal to 11 halves. So we get this system because we're comparing the coefficients of root 5 and the rational part. So this is a really nice system. You think so, right? It is not very nice, but the good part is it is homogeneous. So okay, it's not homogeneous, it's homogeneous. So in other words, notice that the sum of the powers of a and b in each term is always 5. That's what it means. So we can basically replace b with something like ka. So changing the variables here. And when we do, we get the following. We get from the top equation, this is the top one, this is the bottom one. We get 25 a to the fifth plus 50a cubed k squared a squared plus 5a k to the fourth a k to the fourth a to the fourth, and then that is divided by, I'm going to divide both these equations side by side because my goal is to what's it called, get rid of some stuff because this is homogeneous, so you know it'll be nicer that way. So now I can set it equal to something nicer because here we can take out a to the fifth powers. That gives me the following. Again, without further ado, let me give you what it is in the interest of time, because we don't want to make this video way too long. K to the fifth plus 125k plus 50k to the third power. And then a to the fifth power cancels out. And since we're dividing them, the 1/2 cancels out, and we end up with 5/11. Great. Well, let's go ahead and distribute. We get 5k to the fifth. If you're still here, we're going to solve another quintic, but this time it is going to be a good quintic. I'll tell you why. And 55k to the fourth power. And let's put everything together. 5k to the fifth minus 55k to the fourth power plus 250k to the third power minus 550k squared plus 625k minus 275 is equal to 0. Phew. That was some equation. Now, in this equation, have you noticed that the sum of the coefficients is 0? You probably didn't, but anyways, you can check. K equals 1, yay! Okay, great. So now if k equals 1, this means why? Because the sum of coefficients is 0. From here we get b equals a. Remember, our assumption was b equals, what was it? B equals Ka. Yeah, I found it. Okay, B equals Ka. So since K equals 1, that means B equals A. If you plug into the equation, like replace B with A, you get A to the 5th plus 125 A to the 5th, which is awesome, plus 50 A to the 5th equals 11 halves. From here, you get 176 A to the 5th power equals 11 halves. I noticed that 176 is divisible by 11, and it's 16 times 11. So this gives us, A to the 5th equals 1 over 32. Nice. And this, from here we get A equals 1 half. Since A equals B, B is also equal to 1 half. But our assumption was that our expression, which was the 5th root of 5 root 5 plus 11 over 2, can be written as A root 5, 1 half root 5, plus B, which is 1 half, or just root 5 plus 1 over 2. This means that the other guy, which is kind of like the conjugate, not conjugate, but kind of, you get the idea. It is going to be root 5 minus 1 over 2 because the sign is going to change from binomial theorem. Now I have to add these two guys up so that I get root 5 plus 1 over 2 and root 5 minus 1 over 2, and the 1 cancels out, and I end up with root 5. And this almost brings us to the end of this video because I want to show you some numerical values. Yay! This is the real solution. We talked about it. And these are the other complex solutions if you want to proceed with the complex solutions to this expression. But obviously, this is a real number for reals. And this is the answer. And I kind of checked the result because I wasn't sure. And yeah, they're pretty close, right? And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you tomorrow with another video. Until then, be safe, take care, and bye-bye.